Hello. In today's lesson, we will discuss the first law of thermodynamics. What does the laws of thermodynamics describe? When heat is supplied to a system, now understand a system as an amount of gas enclosed in a container. If you give that system a certain amount of heat, what happens to the system? Well, from our earlier discussions, you know that heat is a measure of the total internal energy of a system. If you supply heat to a system, the internal energy of the system will increase. And internal energy can be potential and kinetic. Now, when you consider a gas at a low density, you can imagine that the intermolecular forces will be very small. If you remember the assumption we made, that means the potential energy increase can be neglected. Most of the internal energy or all of the internal energy change will be the translational change in the internal energy. And I hope you remember the equation for the internal energy we derived earlier. Also, the amount of heat given can actually expand the gas so that the gas can do work. So these are the two things can happen. What are the two things? The internal energy can increase, also the gas can expand and do work. Now, the first law of thermodynamics is actually a statement of the law of conservation of energy. What does that mean? Energy can neither be created nor destroyed, but it can be changed from one form to another. A certain amount of heat energy can be made to do work. In fact, you are able to drive to school because heat can do useful work. You see that? So all those are involved in the first law of thermodynamics. When heat is added to a system, it can result in two things. We talked about that. It increases the internal energy of the system, and we will represent the increase in internal energy as delta U. And it results in the system doing work. The gas can expand and do work. Delta W. So, if delta Q is the quantity of heat added to a system, what is that delta Q equal to? You see, according to the conservation of energy, this amount of energy has to reappear in other forms. What are the forms? Increase in the internal energy and the work done. So delta Q equal to delta U plus delta W. It's a very important statement, and this is actually a statement of the conservation of energy, and that is the statement of the first law of thermodynamics. So this statement of the first law of thermodynamics establishes a direct relationship between heat and mechanical work. Now, this statement suggests that mechanical energy can be converted to heat. Now, can mechanical energy be converted to heat? What happens when you rub your hands? Mechanical energy, energy of motion, is becoming heat energy. And heat energy can be made to do work. And we have in our industrialized society a lot of examples around us where heat is made to do useful work. Now, while W is a measure of the work done by the system, negative W is a measure of the work done on the system. You must distinguish those two. Work done by the system as a result of the heat supply, and work done on the system. You pump, using a pump. If you pump down, you are doing work on the system. That will be represented by negative W. The internal energy U is a function of the state of the system. What does that mean? The state of the system. The pressure, volume, and temperature. So just as P, V, and T are functions of the state of the system. So along with P, V and T, we will now add one more, that is the internal energy. When a gas is compressed, for example, its states, namely P, V, T and U, will change. All those are likely to change: pressure, volume, temperature and the internal energy. For a small quantity of heat dQ added to the system, the law can be written as dQ equal to du plus dW. Well, it's not different from delta Q equal to delta U plus delta W. The same equation. Let's do a small problem. If 1.68 times 10 to the 6 joules of heat energy is added to a gas that expands and does 800 kilojoules of work, what is the change in the internal energy of the gas? Well, it's a direct application of the statement of the first law of thermodynamics. You have delta Q given, the amount of heat added. You have delta W given, the amount of work done. Therefore, we can find delta U, the change in the internal energy. So dQ equal to 1.68 times 10 to the 6 joules. dW, the work done, is 8 times 10 to the 5 joules. dQ equal to du plus dW. Therefore, du is dQ minus dW, which is, this is dQ, this is dW, and that's equal to 8.8 times 10 to the 5 joules. A very simple, down-to-earth problem. Let's try another one. At Niagara Falls, the water drops 50 meters. If the change in potential energy goes into the internal energy of water, a very good example of how stored energy can be converted to heat energy. You see, at the top of the fall, the water has potential energy, and all that water, when it falls, the energy becomes kinetic, becomes internal energy, or the increase in temperature. What is the increase in temperature of water? Now, let's consider m kilogram of water at the top of the fall. Now, look at my diagram. This is supposed to be the Niagara Falls, big water and falling to the bottom. All right? Now, let's say m kilogram of water falls to the lower level. What is the potential energy of that m kilograms of water when it is at the top? Is mgh. That is the potential energy. So U equal to mgh at the top. And when it falls to the ground level, its potential energy will be 0. All that energy has now become the internal energy delta U. You see, all the energy, all the potential energy at the top has now become internal energy of water. So we say delta U equal to mgh. All right. Now, if delta theta is the change in temperature of water, its increase in internal energy. Now, do you remember what is the increase in internal energy of m kilogram of a substance? In other words, the amount of heat added to it. Mass times specific heat times change in temperature. So, we've got dQ equal to mc delta theta, and that change in the internal energy must be equal to mgh, the original potential energy. Is that right? Now, if you look at here, you can divide both sides by m. M will disappear, and solve for delta theta. Delta theta equal to gh divided by specific heat of water. Well, g we know, 9.8 meters per second squared. H is the height from where the water falls, and that is given to us. specific heat of water is 4,180 joules per kilogram per Kelvin, and that's equal to 0.12 Kelvin. Not a big increase in temperature, but a measurable kind of temperature increase. Another problem. A lead bullet, initially at 30 degrees Celsius, just melts upon striking a target. Can you imagine that? A lead bullet, because it is traveling so fast, it is brought to rest. That means all the kinetic energy becomes internal energy. And that internal energy is just sufficient to melt it. Assuming that all the initial kinetic energy of the bullet goes into the internal energy of the bullet to raise its temperature. Calculate the speed of the bullet upon impact. What was the speed of the bullet when it struck the target? Melting point of lead is 327 degrees Celsius. Latent heat of fusion for lead is 2.47 times 10 to the 4 joules per kilogram. And specific heat of lead is 128 joules per kilogram per Kelvin. Alright, it's a very simple problem based on what we did in our previous class. So, we start by assuming that let the speed of the bullet be v when it strikes the target. And let its mass be m. The kinetic energy K upon impact will be therefore 1/2 mv squared. K equal to 1/2 mv squared. And we are told that all this kinetic energy is changed into internal energy of the bullet. Alright, so this energy is used to raise the temperature of the bullet to its melting point of 327 degrees. So from 30 degrees, the internal energy supplied it increased the temperature from 30 degrees to 327 degrees, and then it melted it. Alright, so we can say 1/2 mv squared, the initial total kinetic energy, is used in increasing the temperature of the bullet from 30 degrees to 327, and the amount of heat used to do that is mass times specific heat of lead multiplied by the change in temperature. And then what happened? After lead has reached this melting point, it has been converted to liquid lead. The amount of heat needed to do that is mass times latent heat of fusion. Now, in this equation, m appears in all the terms, so it gets cancelled. That's why I used the red coloring there. Cancelling m, we have 1/2 v squared equal to, I replace the values. The specific heat of lead is 128. Delta theta is 327 minus 30, the change in temperature, plus latent heat of fusion of lead is 2.47 times 10 to the 4. Now, in this equation, there is only one unknown. We can solve for that. Now, the right-hand side, I simplified. I got 62,716, and that is 1/2 v squared. Therefore, v squared equal to twice this. And therefore, v is the square root of that, and that is 354 meters per second. It's a beautiful problem illustrating the measurement of heat we did in the previous class and the conservation of energy that we are now doing today. Alright, I want you to look through this problem one more time. One more example. A small immersion heater is rated 550 watt. An immersion heater is a coil of wire. You immerse it into water and turn it on. The water will get heated. We say the heater is 550 watt. Now, what is a watt? Watt is the unit of power. It is joules per second. So, it is rated at 550 watt, means it produces energy at the rate of 550 joules every second. So when you put that heater in water, the heater will supply 550 joules of heat every second. That's what it means. How long will it take to heat 200 grams of water from 20 degrees to 100 degrees Celsius? Assuming that 90% of the heat produced by the heater is used in heating the water. Alright, what do? The heater is rated at 550 watt, means that it supplies 550 joules of energy to the water every second. Now, we need to find the time. Is that right? We need to find the time. How long will it take? So, let's say let the time taken to heat the water be T seconds. So, if the heater produces 550 joules of energy every second, what is the amount of energy produced in T seconds? It will be 550 T. That is the total amount of energy produced by the heater. And only 90% of that heat is used by water in heating it. So 90% of this will be 0.9 times 550. So the amount of heat Q used in heating the water is 90% of this. That is 0.9 times 550 T. That is 495 T. That is the amount of heat supplied to water. Now, water receives that amount of heat and increases its temperature from 20 degrees to 100 degrees. Can you write an expression for that? What is the quantity of heat received by water to increase its temperature? Well, the amount of heat energy needed to heat 200 grams of water from 20 degrees to 100 degrees is Q equal to mc delta theta, where C is the specific heat, delta theta is the change in temperature, m is the mass, and that will be m is 0.2 kilogram, specific heat is 4180, and delta theta is 80, is that right? From 20 degrees to 100 degrees. Now, and this is now equal to 66,880 joules. Now, this is the amount of heat actually used by water. And where did this come from? It comes from the heater. 495 T is the amount of heat produced and supplied to water, where T is the amount of time taken to do this. And we need to solve for T. So this gives T equal to 135 seconds, which is 2.15 minutes. Another very useful type of problem. Alright, we are now going to look at internal energy of an ideal gas. Internal energy of an ideal gas. In lesson 2.1, if you remember, we obtained an expression for the kinetic energy K of n moles of an ideal gas. Does anybody remember that expression we derived? K equal to 3/2 nRT. And for an ideal gas at low density, its internal energy depends only on the temperature. There is no change in the potential energy. So all the heat supplied will go into raising the temperature. This is because at low densities the intermolecular forces can be neglected. That is one of the assumptions we made in the kinetic theory of gases. Thus the internal energy of a gas is just the translational kinetic energy given by U, the internal energy, equal to 3/2 nRT. Well, that's a review we just talked about some time ago. Let's now look at the relation between work and the PV diagram for a gas. What is the meaning of PV diagram? PV diagram is simply a graph drawn with P on the vertical axis and V, the volume, on the horizontal axis. A graph drawn of pressure against volume. Alright. The figure shows an ideal gas enclosed inside a cylinder. Now here I have a cylinder and a piston. Everybody is familiar with that, is that right? Your car has many cylinders and pistons, and there is a gas enclosed inside the cylinder. It's a tightly fitting piston. The pressure of the gas is P and its volume is V. The pressure is P. Now this is the gas enclosed. This is the colored part, is the piston. This is the gas. And the gas applies a pressure P on the piston. Now, if A is the area of the piston, tell me what is the force acting on the piston. Now, suppose if this is the area, if the pressure is P on that area A, the total force will be pressure multiplied by the area. Is that right? I hope you know that, because pressure is force per unit area. Therefore, the total force will be pressure multiplied by the area. So the force exerted by this gas on the piston is F equal to P times A. And if you are now able to move this piston as a result of this force, it means the gas is doing work. Is that right? Because it is the pressure exerted by the gas that is now applying this pressure on the piston, trying to move it. If the piston moves through a distance dx, you see, this is the initial position of the piston, it moves through a distance dx. Now, what is the work done by the gas? The work done, dW, can be written as, how would you write it? Force multiplied by the distance. It will be dW equal to F dx. But F equal to P times A. So that will be P times A, that is F, times dx. Now tell me, what is A multiplied by dx? A multiplied by dx. Now, if this is the piston side, imagine it's completely covered. Now, this is dx. This is the area. That area multiplied by this dx actually gives you the volume of this. Or we can call it dV, is that right? The increase in volume. So A times dx is the volume of that space. So I'm going to call it P times dV, where dV is the increase in volume. So watch this. The work done by the gas inside the cylinder is a measure of P times dV, pressure multiplied by the change in volume. Alright, so that will be A dx equal to dV. Now, the total work done when the volume changes from V1 to V2, if the volume changes from an initial value V1 to a final value V2, then dV, the change in volume, will be V2 minus V1. Therefore, we can write W, the work done by the gas, is P times V2 minus V1. Now here, the assumption we made is that the pressure remains a constant. Then only this will work. Now, a process where pressure remains a constant is called isobaric process. In an isobaric process, pressure remains a constant. So, what is the equation for work done in a system, or work done by a system where the pressure remains a constant? Or what is the equation for work done in an isobaric process? W equal to P times V2 minus V1. The constant pressure multiplied by the change in volume. Now, I can represent that on a PV diagram. Look at the PV diagram. The pressure on the vertical axis, volume on the horizontal axis, and the pressure remains a constant. So this is the pressure, and that remains a constant. Volume changes from an initial value V1 to a final value V2. So tell me, what does the quantity P times V2 minus V1 represent? Why have I shaded that region? This is the value P, the constant pressure. And V2 minus V1, I'm sorry, that is not P. P is this length, because pressure is on the vertical axis. So this length is the constant pressure, and that doesn't change. As we go on, pressure remains a constant. But volume changes from V1 to V2. So this length or that distance is V2 minus V1. So what is P multiplied by V2 minus V1 represent? Well, work done is actually represented by the area under the PV diagram. So work done in an isobaric process is P times V2 minus V1, and this is a measure of the area under the PV diagram. Well, the area, what does it mean, area under the PV diagram? This red line is the PV diagram. It's the plot of pressure against volume. Pressure remains a constant and volume changes. Volume changes from V1 to V2. The value P times V2 minus V1 is given by the area under the PV diagram. Very important. It is applicable in any situation. The work done by a system is given by the area enclosed by the PV diagram. All right. Now, pressure volume, which is PV diagrams, are a primary visualization tool for the study of heat engines. Now remember, all of you drive heat engines. Your car is driven by a heat engine. And here you have the PV diagram for your heat engine. Now let me see if I can spend a couple of minutes to show you how the car engine really works. Now your car engine has a cylinder. Watch what I'm drawing here. The car engine has a cylinder. This is the cylinder. And a piston moves inside the cylinder. Now what happens is, you have something called valves in your car. A valve opens and a mixture of air and fuel is fed into here. That means the volume increases, is that right? The volume is actually increasing and the gas is fed in here, and that is actually represented by this part. The volume increases and the pressure decreases. Now, what happens next is the piston is now made to move backward by applying, well, that's what your battery does in order to start your car. Now, the piston is moved back. What does that mean? It means the volume decreases. What's this? The volume decreases and the pressure increases. You see that? The volume decreases and the pressure increases. And that will bring the piston to somewhere here. Let me draw that here. The piston will come somewhere here. So all this gas, the original volume that much, is now compressed into that volume. So that much of original volume of gasoline and air mixture is now being compressed to a very small volume. What happens? The pressure and temperature increases. And it is at that time you add a small amount of heat. How? Your spark plug will produce a spark. And what happens is a great explosion. And that great explosion will throw the piston back. And that is when your car comes to life. Say your car is started. The great explosion there produces a great amount of energy. That is the useful work done. Look at this part of the diagram. The volume increases, the piston is pushed back. The volume increases, the pressure decreases, and then the used gas is thrown out into the exhaust, and the cycle continues again. That is how your car engine works. Alright, let's move on from here. It's nice to know how the car engine works, is that right? Since the engines usually involve the gas as a working substance, and in the car it is a mixture of gasoline and air. The ideal gas law relates to the PV diagram to the temperature, so that the three essential state variables for the gas can be tracked through the PV diagram. Since work is done only when the volume of the gas changes. Look at this. Work is done only when the volume changes. That means it changes from, on this leg, from 2 to 3, there is useful work done. Now, is there any useful work done during this time? 3 to 4. There is no change in volume, therefore there is no work done there. But from 4 to 1, there is work done. But if you notice the direction, if from 2 to 3 work is done by the gas, from 4 to 1 work is done on the gas. So if this is positive, that is negative. So what is the useful work produced by the system is the difference between the two, and that's why it's been shaded. So the only amount of useful work your car engine does is that much. Remember, work done is the area under the PV diagram. So let me go and shade that for you. Now, the whole of this area, is the work done by the gas. And this area, the area below the logo graph, that's the area work done on the gas. You see that? Work done by the gas, work done on the gas. So the useful work done is the work done by the gas minus work done on the gas, which is that shaded area. Alright, let's continue from there. Now, let's have a look at if it is possible to see how the car engines really work. Now, most small cars have got 4 engines, 4 cylinders, is that right? Well, I hope you have some idea of how these systems actually work. I will see if I can show that to you. Now, watch how the different cycles work in the 4 cylinders, one after the other. Now, watch just one cylinder. Engine getting compressed, spark plug fired, useful work done. That is the exhaust. You see, now let's look at this. Alright, that's when the gas is intaken. Now the piston moves forward, pressure increases, and now useful work done, and the process continues. And the working stroke, out of the 4 strokes the engine has, only 1 stroke produces useful work. And therefore, when you use 4 engines one after the other, the useful stroke for each of these is continuously followed one after the other, so that the energy that is given to the drive shaft is continuous. And that's the reason why your car will not go chuk chuk, it will be continuously moving forward. You've got 4 engines delivering the power continuously. Alright, let's close this and move on. So during the cycle, work is done on the gas by the piston between stages 4 and 1. Work is done by the gas between 2 and 3. The difference between the work done by the gas and the work done on the gas is the area enclosed by the curves. And that is the useful work produced in the cycle. And in a car, this useful work is done by each of the cylinders so that energy is delivered continuously to the drive shaft. Alright. The area enclosed by the cycle on a PV diagram is proportional to the work produced by the cycle. Alright, let's go on. Let's now look at some more of PV diagrams. The figure shows an ideal gas at an initial state of pressure P1, volume V1 and temperature T1 and heated at constant pressure to a state of pressure P1, volume V2, temperature T2. Tell me, what is the work done in that process? Pressure remains the constant, volume changes from V1 to V2, temperature changes from T1 to T2. Work done is a measure of the area under the PV diagram. Is that right? So the work done in this process is the area under the part, which is shaded. Now, then it is cooled. Now, from this state, it is cooled from a temperature T2 to a temperature T3. The pressure is reduced from P1 to P2 and the volume remains a constant. Tell me, what is the work done during that process? Well, during this process there is no work done because there is no change in volume. So work done during this stage is 0 as there is no change in volume. Okay. Now, I'm going to take a different path in the next diagram. Alright, let's see how the next diagram goes. So, this figure now shows an ideal gas at an initial state of pressure P1, volume V1, temperature T1, changed to pressure P2. So, this time the pressure doesn't remain a constant. Pressure changes to P2, volume remains a constant, temperature changes from T1 to T2. Tell me, what is the work done during that process? The work done is 0. The work done for this process is 0 because there is no change in volume. Now, then it is heated from temperature T2 to T3. Pressure remains a constant. Volume changes from V1 to V2. What is the work done during that process? It is the area shaded here. That means if you compare the two diagrams from the previous slide and this, the initial position and the final positions are the same. But because the path we took to arrive at the final positions are different, the net work done is markedly different in the two cases. Let's now look at a change called isothermal expansion. Isothermal, what does that mean? Isothermal. Isobaric means at constant pressure. So what does isothermal mean? At constant temperature. So the figure shows an ideal gas at an initial pressure P1, initial volume V1 and temperature T1, expanding under a constant temperature to a pressure P2, volume V2 and temperature T1. We actually have seen this before. A plot of pressure against volume at constant temperature. Anybody recall what we call that? We call the curve at that time an isotherm. It was an isotherm. Now, since the temperature remains a constant, such a process is called isothermal process. The work done in an isothermal process is given by the area under the graph and can be written. I'm going to simply give you the formula. So take down this formula. Work done in an isothermal process is nRT times ln. ln is logarithm to the base e, natural logarithm of V2 over V1. You must know this formula. I will ask you problems based on that. So work done in an isothermal process is nRT ln V2 over V1. Let's do a small problem, and 1 mole of a gas initially at P1 equal to 3 atmosphere, V1 equal to 1 liter and U1 equal to 456 joules is cooled at constant volume so that its pressure drops to P2 equal to 2 atmosphere. Alright, if you understood the process of that first sentence, it is cooled at constant volume. Can you tell me what is the work done during that process? When there is no change in volume, there is no work done. So for that process, there is no work done. Alright, what happens next? It is then allowed to expand. Well, it is then allowed to expand. That means work is done. At a constant pressure until V2 equal to 3 liters and U2 equal to 912 joules. V2 is the final volume, U2 is the final internal energy. A. Show this process on a PV diagram and calculate the work done by the gas. B. Find the heat added during this process. Alright, watch carefully the steps for this problem. Let's now do it on a PV diagram. Let's draw the PV diagram. What's the beginning state? Initially, the gas is at P1 equal to 3 atmosphere. Look at it. This is the pressure, the vertical, volume, the horizontal. The pressure is P. Pressure P equal to 3 in the beginning. Volume V1 equal to 1 liter. So this is where the gas is initially. What happened to it? And its internal energy is 456 joules at that instant. It is then taken at constant volume to P2 equal to 2 atmosphere. And then it is allowed to expand. You can see, it is then allowed to expand at constant pressure. So the pressure now remains at 2 atmosphere. It expands from V1 equal to 1 liter to V2 equal to 3 liters. So this is where the gas is now. It expands at constant pressure to a volume of 3 liters. And its internal energy now is 912 joules. Show this on a PV diagram. We got the PV diagram there. And calculate the work done. How do you calculate the work done using the PV diagram? Well, the work done is the area enclosed by the PV diagram. During the first process, there is no work done. Work done happens only during the second process. What is the area enclosed in this case? The work done is given by the shaded area, and that will be W equal to P dV. P is 2 atmosphere, dV, the change in volume, is 3 minus 1, that is 2 liters. So work done is 2 atmosphere times 2 liters. Well, in order to get W, the work done in joules, the pressure in atmosphere has to become pressure in Pascal. Now, how do you convert atmosphere to Pascal? We have done that before. Multiply by 1.01 times 10 to the power 5. 1 atmosphere is 1.01 times 10 to the 5 Pascal. And converted liters to meter cube. How do you convert liters to meter cube? I did that in the last lesson. A liter is 1,000th of a meter cube. So, 2 atmosphere is 2 times 1.01 times 10 to the 5 Pascal, and 2 liters is 2 times 10 to the negative 3, and that will be now in joules. So the work done is 404 joules. Next, find the heat added during this process. Alright, what's the equation for heat added? dq equal to du plus dw. What is du? The change in the internal energy. The original internal energy U1 is 456 joules. The final internal energy is 912 joules. So the change in internal energy is 912 minus 456, and that is 456 joules. Now the heat added is dq equal to du plus dw. We now know du, the change in the internal energy. dw we just calculated in the previous slide, is that right? Yes. And so that will be 456, that is du, plus 404 joules is the work done. And so the total heat added is 860 joules. A very representative problem. Let's try another one. 1 mole of an ideal gas at P1 equal to 3 atmosphere, V1 equal to 1 liter, and U1 equal to 456 joules is heated and allowed to expand such that it follows a straight line path on a PV diagram to P2 equal to 1 atmosphere, V2 equal to 3 liters, and U2 equal to 912 joules. Show this on a PV diagram and calculate the work done by the gas. Again, find the heat added during this process. Alright, is it difficult to draw a PV diagram for this? I have given you the coordinates, so just use them. Now here, what is the initial state? Pressure on the vertical, volume on the horizontal. Initial pressure is 3 atmosphere. Initial volume is 1 liter, so the gas is here. Pressure equal to 3 atmosphere, volume is 1 liter. And of course the internal energy is 456 joules. Is heated and allowed to expand so that it follows a straight line path to pressure P2 equal to 1 atmosphere, V2 equal to 3 liters. Alright, what is the work done? The work done is the area under the PV diagram. What is the area under the PV diagram here? The area, the shaded area, can be divided into a rectangle and a triangle. Alright? So the shaded area is made up of a rectangle and a triangle. Can you calculate the area of the rectangle? The length of the rectangle is 3 minus 1, and that is in liters. And the width of the rectangle is 1 atmosphere. Let's go and do that there. So, for the rectangle, that will be 1 atmosphere. This is 1 atmosphere times 2 liters. That is the area of the rectangle. Plus. Now, plus what? Plus the area of the triangle. What is the formula for area of the triangle? 1/2 base multiplied by height. Now, what is our base? Our base is 3 liters. And our height is 2 atmosphere. Is that right? 3 minus 1. So that will be 1/2. 0.5 is for 1/2. 1/2 base. Base is 2 liters. And the height is 2 atmosphere. Alright. That will be 1 multiplied by 2 is 2. So that will be 2 atmosphere liter plus, this again is 2 times 2 is 4. 4 times 0.5 is 2. 2 atmosphere liter. And that gives me 4 atmosphere liter. Can you now convert atmosphere liter to joules? How? Convert atmosphere to Pascal, multiply by 1.01 times 10 to the 5. Convert liter to meter cube, multiply by 10 to the power of -3. So that is 4 times 1.01 times 10 to the 5. That makes the atmosphere to Pascal. And times 10 to the -3 makes liters to meter cube. And that will be Pascal times meter cube is joule. And that's equal to 404 joules. So the work done during this process is 404 joules. What is the heat added during this process? Well, we now know the work done. And do we know the change in the internal energy? Yes, the change in the internal energy. We know U1, we know U2, therefore du is U1 minus U2, that is 456 joules. Therefore dq, the heat added, is dw plus du is 860 joules. You notice the previous problem and this problem has the same result. Although the path followed is different, the total heat added remains the same. Okay, let's do another problem. An ideal gas initially at 20 degrees Celsius and 200 kilopower, watch the units carefully, has a volume 4 liters. It undergoes a quasi-static isothermal expansion. You don't need to worry about the meaning of quasi-static. Just concentrate on isothermal expansion. What does it mean? The temperature does not change. Until its pressure is reduced to 100 kilopower. Find the work done by the gas and the heat added to the gas during the expansion. Well, let's pick our data. The initial temperature is 293 Kelvin. The initial pressure is 200 kilopower. Is that right? That will be 200 times 1000 Pascal. Initial volume is 4 liters. Final pressure is 100 kilopower. And now, let's use the ideal gas equation PV equal to nRT and obtain the number of moles of this gas. The number of moles N equal to PV over RT. And I use the value of I use the values of P1 and V1, the initial state. So that's P1, V1 divided by RT, and the T1 is given to us. And that gives you 0.328 mole. So the amount of gas is 0.328 moles. Why do we need that? Well, you know that for an isothermal process, you see, isothermal process obeys Boyle's law, isn't it? Pressure is inversely proportional to volume when temperature remains a constant. Temperature remains a constant is isothermal. So Boyle's law is the law for isothermal process. For an isothermal process, P times V is a constant, or P1 V1 equal to P2 V2. Now, therefore, what is V2 equal to? V2 equal to P1 V1 divided by P2. That will be 200 kilopower multiplied by 4 liters divided by 100 kilopower. See, I have left all the units the same way. Kilopower divided by kilopower is a ratio, it doesn't matter. And the volume V2 will now be in liters. That's equal to 8 liters. Now look at the steps we took to find the final volume. Why do we need the final volume? If you understood and kept track of the formula I gave you, what is the formula for work done in an isothermal process? Anybody recall the equation I gave you? I gave it to you here, asked you to remember it. Work done in an isothermal process is nRT ln natural log V2 over V1. So we need the number of moles of the gas, we need the volumes V1 and V2. We were given V1, we now found V2. And so W isothermal, work done in an isothermal process, is nRT ln V2 over V1. And n, the number of moles we calculated, is 0.328 moles. R is 8.314 joules per mole per Kelvin. And T is 293 Kelvin. There you are. ln V2 over V1. Now, because it is a ratio, it doesn't matter the unit in which you measure it. So that will be ln of 8 over 4. And put that in your calculator, it will give you 554 joules. The work done during this process is 554 joules. If that is the case, what is the heat added? Well, heat added dQ equal to dW plus du. Now tell me, this is an isothermal process. That means the temperature does not change. Therefore, what is the change in the internal energy? If the temperature does not change, the internal energy does not change. So for an isothermal process, du equal to 0. Therefore, dQ equal to dW, the amount of heat added equal to 554 joules. Alright, well, that has been a quick way to discuss the laws of thermodynamics. We only discussed one law, the first law of thermodynamics. Now, I'm going to leave the second law. Most of you do a chemistry course. That will be discussed in chemistry course. Well, I will see you for next lesson later on.